đẹp. Ok, không có lại.
Alright guys, welcome to my talk. Today my name is Phú Võ. Today I will talk about the dehydrogenation of propane catalyzed by 6 nanometer platinum cluster. So there are three topics that I will address today. The first one is the significance of dehydrogenation of propane. The second one is about the experimental and theoretical study. The first one is the conclusion. So why are we interested in dehydrogenation of propane? Because once the propane turns into the propene, it can be used in various ways. Some characteristic of propene is high chemical corrosion resistant, and it's easy to machine and cut. It's lightweight, very easy to maintain and clean, excellent eruption resistant, and low moisture absorption. So as you can see, the propene can be used to make the stuff that's very common in our life, such as the gloves that you wear in the winter, and the chair that you sit on, or even the acetone that we stand the color of nail for women, sometimes for men. So I will talk about the platinum cluster, the study of platinum cluster theoretically and experimentally. In the theoretical study, I will talk about the mechanism and the Gaussian software that we use to run the method. Experimental study, I will talk about the apparatus mass selected for the cluster. Talking about the mechanism, Banda and his college proposed there are like 4 steps in the dehydrogenation. I will walk through the 4 steps. So here's the energy diagram. This molecule represents the PT4 cluster, and this one is the propane. So once the PT4 contact with the propane, it will try a way to remove the hydrogen and form a bond to the carbon atom of the propane. The second step is very similar to the first step. The PT4 cluster find a way to make a bond to the another second carbon atom and take away the hydrogen of the propane. So after that, in the presence of oxygen, the oxygen get absorbed and decomposed decomposed on the PT4 cluster, and then the oxygen take away the 2 hydrogen on the propene to form the water and release heat. On the final step, the heat that released provide energy in form of vibrational motion to separate the 2 compounds. So we have, so in this one is the overall net equation, net reaction. So you can see there's no PT4 in here. So that's mean because it's the catalyst. So by when you see this graph, and you can see like on the first step, it has to overcome the energy barrier. So it is the very limiting step. So they use the density functional theory to determine the charge of the PT cluster and the size of the PT cluster, because those two characters have a big effect on the catalytic ability. The Gaussian software is used in this computational method, like a computational study. So there are four main methods that's used to for the software. The one is B3 lift, B3 PW91, PVE PW91. So they use the Gaussian software to run the calculation on each apply the each of the method, and they calculate the electron affinity, ionization energy, and the bond energy in kilojoule per mole. And here's the data showing the error, showing how different between the calculated data and the experimental data. So after they construct the table in the reverse line, they get the mean of the absolute error, and they make a graph to compare and to see like which one they get the lowest error. And they see that the B3 lift, it has the lowest error, which is the most reliable to use to calculate the data. After that, after knowing which method is used, they run the calculation and to determine which charge between the neutral charge or positive charge plus the which one is better. And on the left is my graph of neutral cluster, and the right, and this one is the positive one cluster. And as you see that on the transition state, most of the cluster concentrate on the energy barrier. One of them get higher than the energy barrier. However, for the positive one cluster, none of the cluster above the energy barrier, and especially the PT2 has going downhill, which is really good. So they say that they conclude that the positive one cluster has more reactive than the neutral one. What about the experimental study? So in the experimental study, they use the apparatus to select the mass of the cluster, and let's look. And the cluster must be performed in gas phase. And let's look at the apparatus. So this is the platinum junk, and then they use that to as an input, and then the PT junk got heated up into the gas phase, and then it's transferred through here into the quadruple mass selector. In here, they're using the electric magnetic field to select the specific side of the cluster, and it got collect on the substrate holder. So at first, when they isolate isolate the smaller PT cluster, this was a problem because when the PT cluster get isolated, they tend to amalgamate together. That's why they come up with the idea that they deposit the PT cluster into the membrane support. So here's one of the example of the support membrane. This one is the aluminum oxide membrane, and they find that this is the PT cluster very stable when you deposit on the membrane. And then they do the experiment to investigate which side of the PT cluster is the best. It's not the best, it's better. And they see that the PT 8 to 10 is really good for the reaction. And for the supporter membrane, they see that the withdrawing withdrawing electron membrane is better than the donating electron membrane. In a conclusion, the small platinum cluster are active catalysts for propane dehydrogenation. For the property of the cluster, PT cluster, for the size, the sub-nanometer size is referred. For the charge, the positive charge PT cluster is more active than the neutral PT cluster. For the surface of the support membrane, the withdrawing surface is supposed to be better than the electron donating surface. I want to have a special thanks to Central Washington University Chemistry Department and Dr. Ge to providing me this opportunity for the talk. Any question you would like to ask me?
So when you're doing the experimental part with the apparatus, you said you have to do it in gas phase. Is that right?
Yes, I believe so.
Yeah. So can you do it in? Well, my first question is, if you're doing it in the gas phase, is there like a specific temperature that you're supposed to do it at? And the second question is, can you do it in like a solid phase or some type of other phase?
About the temperature, they say that the PT cluster is stable stable between 40 degrees Celsius to 400 degrees Celsius, and because it has to be performed in gas phase, because in the gas phase the PT cluster can be like pure, it cannot react with the other stuff.
So you said that this PP cluster can break a carbon-hydrogen bond, right?
Yeah.
Can this PT cluster break a carbon-carbon bond. You have propane, there are carbon-hydrogen bonds, and carbon-carbon bonds. So can this heating cluster break a carbon-carbon bond? If the answer is yes, then compare this difficulty between breaking a carbon-carbon bond and the difficulty of breaking a carbon-hydrogen bond.
I think it can be possible to break the carbon-carbon bond, but the problem is that you need to find another PT, another side PT cluster that can highly react to break the carbon-carbon bond. And to compare about the energy, to break the carbon-carbon bond, it requires a lot of energy. So a lot of energy compared to the breaking the carbon and hydrogen bond.
I have another question. We all know that bulk platinum is stable, so it's used to make jewelries. Why does platinum clusters are so active in catalyzing the carbon-hydrogen bond breaking reaction?
Okay. So so here I just see like this bulk platinum is very condensed. The PT cluster is very condensed, and it's inert to the reaction. And if you break it into the small pieces, it has the more surface to react with another stuff.
Another reason is if you have a bulk, each platinum atom has a coordination number of 12. But then if you look at PD4, each one has a coordination number of only 3. So that means it's under-coordinated, so it's more reactive. And also your answer is correct. You have larger surface.
Okay.
So which came first, the experiment or the calculations?
I think like they exist at the same time. Maybe one first, the other second, but we might not know. So they use like both the experimental and theoretical study at the same time to investigate the PT cluster. I can. So the hand.
No, we did not smile.
So I see that there's a detector, but with the diagram you're just separating the clusters onto that substrate. So did they ever directly use the detector, or was it always just an assumption based off the setup, like the size fraction was landing on the substrate?
So you mean like how do they?
Yeah, because I see that there is a detector, but the particles aren't going to the detector.
You mean the
Yeah.
detector here and although this detector is just for the whole process, whole complex. It might go this way too. Oh, no, it's going to go this way because they use the electromagnetic field to isolate the PT molecule. So the big PT molecule will be collide to be then absorbed to the orbital mass selector, and the smaller one will be reflect to this one. So it's all calculated. This one just the label.
Okay, let's move on. Are there no more